Okay, welcome back. Happy Wednesday. Today, we are going to cover convergence of series, something called the integral test. This is going to be basically the first of many tests that we're going to talk about to determine whether a given series converges or diverges. Remember, a series is a sum of infinitely many numbers, and our question at the end of the day is if you add infinitely many of these numbers, do you get infinity or do you get something finite? Last class, we saw a geometric series and a very simple formula, the a over 1 minus x. For geometric series, we have a way to calculate the actual sum that is very rare. Most of the time, we're going to have to content ourselves with saying, yes, the series converges to some finite number, but we don't know what it is. Or the series diverges to infinity, and that's it. Okay? So most of the time, we are not going to know what it converges to. We are basically just answering a yes or no. It converges or not. Which is great, right? It's only two possible answers for almost all of our questions. Okay, hopefully you're still working on the project. It is due 1 week from today. Any questions? Excellent. Flip a coin. Okay, let's jump in here. Number one. Okay, so we talked about what it means to say a series converges. So let's look at the first few terms of each of these four series here. We'll make some conclusions and recognize there are some things that we don't know how to do at this moment. So let's write out the first few terms. When you plug in n equals 1, 2 minus 3 on top, that's negative 1. 5 plus 9 on the bottom is 14. First term is negative 1/14. Yes? Then we're going to plug in n equals 2. When you plug in n equals 2, maybe this table can plug in n equals 2, and you guys can plug in n equals 3. I just want the fractions real quick. Don't need a calculator here. Somebody else at that table can confirm or deny. Anybody have? The top is not quite right here, Nick.
Yeah,
it's 25, right? Okay, I think that's good. Okay. All right. So we've got these numbers that doesn't appear to be like some easy pattern. It's definitely not a geometric series where you keep multiplying by the same number. But the fact is, I want to know like what's happening like way out here. Meaning, what happens if you send n to infinity in that fraction? What do you get? It is negative infinity over infinity, which means we got to do more work. You could do L'Hopital's. This one's even simpler though because it's the same. Yeah, you could do L'Hopital's, but it's the same power, right? The plus 9 makes hardly any difference. The 2 makes hardly any difference. Same power. What is it? Negative 3 over 5 is correct, right? That's like a pre-calculus theorem from way back about horizontal asymptotes. Okay, what that means is that ultimately you are adding negative 3/5 over and over and over again, basically. It's not exactly going to be ever going to be negative 3/5, but essentially it's a bunch of negative 3/5. How many of them? Infinitely many. What do you get when you add negative 3/5 infinitely many times? Negative infinity, right? There's no question that this series right here diverges because you're repeatedly adding negative 3/5. In fact, that same conclusion we made there applies generally. What's the only limit that we could have gotten here? Not negative 3/5. What's the only number where the series would even have a chance of converging? What's the only number you can get here instead of this negative 3/5, where the series, when you add infinitely many of that number, it has a chance of converging 0. That's the only number, right? If this limit were 0.1 or 0.00001, Doesn't matter. If you add infinitely many of those things, you're going to get infinity or negative infinity in this case. So the only one that has any prayer of working is a 0 over here. Okay, we're going to give that test a name that says if the limit isn't 0, diverges, move on. Okay, let's take a look at part B. Writing out the first few terms, 1 over 1 plus 1 over 2 plus 1 over 3 plus dot, dot, dot. What did the terms approach in this case? They approach 0, which means maybe. What it means is there's more work to do. This one should not be obvious. It's possible it converges at the end of the day to some finite number, maybe it's 17. It's also possible that if you add enough of these, you get closer, you get to infinity. We don't know yet. Next one. This is 1 over n squared. Plugging in n equals 1, we get 1 over 1 squared, 1 over 2 squared, 1 over 3 squared. What happens to those terms? They approach 0, which means we don't know. Josh points out, though, they do approach 0 faster. So let me ask you this. Suppose that if I add up all these greens forever, it's finite. Is there anything you can say about purple? If adding up all the greens forever is some finite number, say it's 17, then purple has to be finite, right? Purple is definitely less than green. Okay. What if I tell you that if you add up all these greens, you get infinity? Is there anything you can say about purple? We can't. It could be infinity, but maybe it goes to 0 fast enough, like Josh says, that it's finite, okay? So this purple is another big old question mark. Green and purple are at the heart of what we're after today. Okay, and then this last one here, part D. If we write out the first few terms, when n is 1, that's a power of 0. So that's just 7. Plus, when n is 2, that's a power of 1. I'm actually not even going to bother. What's that? Yeah, it is 14 over 3. I'm not even going to bother writing it that way. I'm going to write it this way. 7 2/3 to the second. What did the terms go to? The terms go to infinity? The terms go to 0 because you keep taking 2/3 of 2/3 of 2/3 of 2/3. So it gets smaller every time. What kind of, that series has a name. We talked about them last class. Isn't this a series where we keep multiplying by, what's the number in this case? 2/3, right? Every term you multiply by 2/3. That's geometric, right?
I don't get how it goes to 0 though, because you're still adding.
I'm not saying that the sum goes to 0. I'm looking at the individual terms like we did with the, yeah, okay. So this is geometric. Remember the way a geometric series converges is if the magic common ratio is between what two numbers? -1 and 1. What is the common ratio here? 2/3. Geometric with x equal to 2/3, and x equals 2/3 is definitely some number between -1 and 1. So what can we say about that series? The series converges. Even more than that, we could actually figure out what it converges to because we've got our fancy a over 1 minus x formula. We're not going to do it now, but like I said, usually the answer is just going to be, yeah, it converges, and that's all we can say. Okay, so going back to the very first example, we saw that the terms up there were approaching -3/5. And the fact is that automatically told us that the series, where we add up all of these -3/5 forever, diverges, right? Clearly the series goes to minus infinity. So here is our first named test for series, the nth term test for divergence. Nth term is just the name of the general term, like a generic term out there. If the limit as n goes to infinity of a sub n, where a sub n are the terms in the series, if that limit is not 0, then for sure the series, when you add up all those a sub n's, diverges. So if your terms do not go to 0, right away you conclude the series diverges, and that's the end of that problem. That particular series has been analyzed. okay? That is a good series test to try right away. Most of the time, you get the limit is 0, which means there's no conclusion, but once in a while, you get lucky and it's not 0 and the problem is done. Okay, so let's explore one of the two series we didn't know about, the 1 over n and the 1 over n squared. A little bit more detail. So that series, the 1 over n, 1 plus a half plus third plus a quarter forever, musically is called the harmonic series. It's so named because the overtones of a vibrating string have wavelengths half, a third, a quarter of the fundamental wavelength of the string. I'm not really a music and math guy. Can you say anything about that, Levi? Like that sentence? Mm-hmm. Okay. And those fractions are like, they have musical importance. Yeah. Okay. And they give us like nice sounding notes relative to the first one. Is that okay? Excellent. We have a former piano tuner in the class, so we take advantage of that knowledge. Okay. Despite the fact that the terms of the harmonic series approach 0, yes, definitely these numbers are going to 0, no question. It turns out that the harmonic series diverges, meaning if you add more and more of them, the series, the sum, approaches infinity. It gets to infinity really, really slowly. Yeah. But it goes to infinity. More and more that you add, the closer to infinity it gets without bound. Okay, let's informally convince ourselves of this fact by approximating this integral. You guys thought you were done with integrals, but you're not. This integral right here with some left rectangles. We're not going to write any formal sentences here. We will on the next page. Okay, there's a graph of f of x equals 1 over x. When I talk about the integral from 1 to infinity of 1 over x, I am talking about the area under the curve, right? So I'll put I equals like that integral represents that area, right? And we saw something called the useful integrals for comparison. That was one of them. Remember 1 over x to the p? Is that area finite or infinite from like a month ago? So this guy right here was on the cutoff between the finite and the infinite, and it was on the infinite side. 1 over x to the p, 1 to infinity. If p was greater than, if p was greater than 1, that series, that integral converged, something finite. But if it's less than or equal to 1, it diverges, it's infinity. So this is just on the cutoff. That red area is just barely infinity. If I make it 1 over x to the 1.1, all of a sudden it's finite. Small change in the curve, big change in the area. Okay. It is just barely infinite. That is a technically precise mathematical term. Barely infinite. Okay. All right. So we agree that the area in red is infinity. That's from way back. We're going to approximate something with, we're going to approximate this area with some left rectangles. So here are a few left rectangles. Between 1 and 2, remember we're going 1 to infinity, so I'm starting at 1. Between 1 and 2, left rectangle says use the left-hand side to determine the height. Between 2 and 3, which point are we using? 2. We're just using consistently the left side. Between 3 and 4, we use 3. We go that. What is the area of this first rectangle here? It is clearly a 1, right? 1 tall, 1 wide. How about the second rectangle? It's a half because the height is on the curve 1 over x, and what x is the important number is 2. So the height is definitely a half, and the base is 1. So that area is a half. How about the next one? It's a third. Good. Okay, so adding up the greens forever, is exactly the same as our newly named harmonic series. It's exactly the same number. Cool. How do the green areas compare to the red? Overestimates, right? Green is definitely bigger than red. But what did we say about red? It's infinite. So what about green? It's infinite. Yes. You add up those green things forever, it has to be infinity. There's nowhere else for it to go. Okay, so we're not going to write anything yet, but definitely that green is infinite. Next page. We're going to play the same game, but we're going to think about the sum of 1 over n squared. Remember that was 1 over 1 plus 1 over 4 plus 1 over 9, etc. We are going to first think about this integral right here, integral 1 over x squared. Here's the graph of 1 over x squared. Josh pointed out for the series that these numbers go to 0 even faster than the harmonic ones. And you can see, yes, this curve is getting closer to the x-axis much quicker than the previous curve. So that red integral represents the area under the curve from 1 to infinity. So it is this area in here. Was that area finite or infinite from the useful integrals for comparison? That's finite, right? The power there is 2. It's bigger than 1. This is finite. Don't know what the number is, but it's finite. You could find the number. Okay, we are going to approximate that finite area by using right rectangles. Between 1 and 2, which point do we use to determine the height? 2. So you go up to 2, over, and down. Yes, that's our first rectangle. Between 2 and 3, we use 3. And between 3 and 4, we use 4. And I'm really having a hard time, I just don't even have enough pixels to represent because this curve is so close to the x-axis so quick. You'll see why. Let's write down the areas of these green rectangles. Between 1 and 2, remember the height of this rectangle was determined at 2. What is the height of this rectangle on the 1 over x squared curve? That's a quarter, right? Plugging in x equals 2. So a quarter high, 1 wide. The area of that first rectangle is a quarter. Between 2 and 3, the height was dictated by 3. What's the height? 1/9 times the base is still 1. Let's do one more here. What's the height of this guy here? That's 1/16. And the area there is 1/16 times 1, which is almost exactly, well, it's this, right? Okay, so we missed the 1, but who cares? If all we want to know is that black series finite or infinite, adding 1 is not going to change that outcome. Okay, how does green, all these green rectangles, how does that compare to the red area? Green is definitely less, right? A bunch less, actually. And we've already established that red is finite. So what about green? Also finite. Okay, technically, again, green missed the first term, but green is finite, and you add 1 to that finite number, and it is still finite. And so that means that the 1 over n squared series is finite. Okay, so really important conclusion here. What did we say about 1 over n when we add it forever? That's infinite. 1 over n squared, finite. Really subtle difference between those two things, but completely different answers at the end of the day. So you need to make sure you do not fall into the trap of thinking, hey, anytime the terms go to 0, when you add them all up, you get something finite. That is not true. It was true for purple. The terms went to 0, and we added them, and we got finite. But it was not true for green. Those terms went to the 0. We added them, and it was still infinity. Okay? The nth term test never tells you a series converges. It can only tell you that certain series diverge, okay? But if that limit is 0, no conclusion. And the term test doesn't say anything. All right. Number 6 is just an aside here. Although we should be convinced that the sum of 1 over n squared converges to some finite number, we have no way of knowing what it converges to. Leonhard Euler was a Swiss mathematician in the 18th century. Mathematical genius of the highest order. He had a way to figure out what the thing added up to, and he came up with pi squared over 6. So if you add on your calculator 1 plus a quarter plus a ninth plus a 16th plus forever, the answer is pi squared over 6. What's that? There's a book in my office that has a very readable proof that this is correct. So if you are interested in reading outside of class, I can lend you that book. Okay, number 7. The informal arguments we made up above, where we just compared to an integral and then drew some left or right rectangles, are formalized in something called the integral test. Suppose that a sub n equals f of n. All right, a sub n, something like 1 over n squared. F of n was 1 over n squared, or in more familiar letters, 1 over x squared. Okay, that's all that is saying. Just saying, consider the appropriate function. We've got to do an integral. If f is decreasing and positive from some point onwards, decreasing and positive, then we can say exactly what we just set up above. If the area under the curve was finite, then the corresponding sum is finite. Whatever the integral does, the sum does. If the area under the curve is infinite, then the sum is infinite. And we don't even have to bother thinking about whether we should use left rectangles this time or right rectangles this time. The fact is, one of those rectangles is going to work. And so you don't even need to think about which one it is. The reason that we needed the function to be decreasing was that if you have a function which goes up and I don't even need to make it go below. If you have a function which goes up and goes down, suppose that I draw left rectangles here. This left rectangle, is it above or below? Below. This left rectangle is above. So even if I know what the area under the black curve is, I can't say anything. There's nothing obvious about the area of the red, right? So that's why we need the function to be decreasing, so that the left rectangles will consistently be above and the right rectangles will be consistently below. Levi. No, any finite number C. The important thing for the area under the curve and for the infinite series, the sum, is the part out at infinity. So even if the function behaves very badly from 1 to a trillion, it's finite between 1 and a trillion. It doesn't matter what the function is, right? And so let's just look from a trillion to infinity. That's where the money is. Okay, all right, let's use the integral test, number 8, formally by writing some sentences, and then these are the kinds of sentences you're gonna need to write in the activities and on the quiz and on the test. Here we go. Let's first do this, this guy right here. So we're gonna formally write up a mathematical proof to show that the sum of 1 over n diverges. This is really the second time this semester where we're writing mathematical proofs. The first time was when you guys used the comparison test to decide if an integral converged or diverged. The good news for the integral test here is that, again, it's the same template for every one of these proofs. All right, here we go. Sum of 1 over n. All right, so we know that the integral of 1 over x from 1 to infinity converges or diverges. That one diverged. Diverges by the UIC. Useful integrals for comparison. The power in this case, the power on the x is 1, which is less than or equal to 1. So that's integral diverged. Okay, next up, we need to talk about the function itself. F of x equals 1 over x. Needs to satisfy 2 conditions every time to use this thing called the integral test. It needs to be decreasing and positive. Is it? 1 over x, is it decreasing? Yeah, think about the curve, right? Is it always positive? Yeah, as long as you're not on the negative side of the y-axis, and we don't care about that side for this example, is decreasing and positive. if we wanted to be more precise than I'm being here, then we should say yes, starting, because that is not true. It's not positive when x is a negative number. Yes, it doesn't matter because we're not using the negative x portion of the function. I should be writing things more formally. I'm not going to force you guys to write them more formally than this here, but you're absolutely right. Like I should say, as long as x is greater than 0. The good news for you is that you don't even have to like write a proof. Like to show something is decreasing, technically you should take a derivative and show it's negative, but you don't even need to do that. Like the functions we're going to be looking at, hopefully it'll be just obvious. Yes, the function's decreasing and positive, but the fact is you just need to say it, that's all. Okay, and so the sum of 1 over n equals 1 to infinity, has exactly the same behavior. So what can we say about that series? It also diverges. Also diverges by the IT, integral test. Feel free to abbreviate just like I did. You don't. It is up to the reader to understand that you are making this connection here between the integral and the sum, and it will be obvious to the reader because you are referencing the integral test. Okay, so that's it. I don't have enough space here to do the 1 over n squared. In fact, how about I just write, I don't know, like 1 over x squared. Does that converge or diverge? Converges, right? By UIC, it's all like the same language. And the function 1 over x squared, is it decreasing and positive? Yeah. And so then what can we say about the sum of 1 over n squared? Also converges by the integral test. So it's like a fill in the blank, and it's like exactly the same template. Okay. So the last thing here is actually not related to any of the stuff that we just did, but it'll be important to us in an upcoming class. So let's do this real quick. It says next class we'll need to be able to find some limits at infinity. Let's find the following limits in preparation for next class. Limit as n goes to infinity of n over 2n squared plus n plus 1 over 1 over n. I know it looks hideous. I promise you that is going to come up in the context of evaluating a series, not just making them up to torture you. We're actually going to need to do limits that look just like that. Yeah. Let's do that first. So the first thing to do when you see a fraction within a fraction is you copy the top guy. You change this big division line to multiplication, and what do we do with the bottom fraction? Just flip it, right? And over 1. Everyone agree? That's just a familiar algebra thing. Fraction within fraction, we do that first every time. And then we'll write down what Levi said, which was that we can just multiply, and the top is just n squared, and the bottom is copied. And this is looking, what's that? Yeah, it is. So this is looking more familiar, right? Because the powers are the same, what is the limit? 1/2, just looking at the coefficients. 1 over 2. That's it. What diverges. Yeah, if I asked you to find the sum of that kind of fraction, then yes, the sum would diverge because 1/2 is not 0. So essentially you'd be adding up things that are really, really close to a half forever, and it's going to go to infinity. Turns out, that's a good observation. Turns out that these limits are, it's not clear what the series is that we're talking about, but it's not the sum of that fraction. It's another fraction that led to this. Good. All right, part B. n plus 1 squared over 2 to the n plus 1 over n squared over 2 to the n. Let's give it a shot. First step is always the same. Copy that first fraction. Times, what's the next fraction? 2 to the n over n squared is good. Okay, now we got to do some algebra. 2 to the n on the top and 2 to the n plus 1 on the bottom. A lot of that cancels. What's left over? A 2 on the bottom is right. There is one more 2 on the bottom than there is on the top. You imagine on the top is a bunch of 2's all multiplied. On the bottom is the same, but one more. And so they all cancel except for a single 2 on the bottom. If that is not obvious to you, then you can do this kind of thing here. When you see x to the a over x to the b, you can subtract, yes, a minus b. And so in this case, when I subtract powers at n minus this n plus 1, what do you get? You get negative 1 if you subtract top minus bottom, which 2 to the negative 1 is a 2 on the bottom. Okay. The other part, okay, I'm gonna FOIL this n plus 1 squared out. You don't actually need to do this, but it's the first time we're doing it, so I think we should do it. So we FOIL the bottom out, and I'll copy the n squared here on the bottom, just making a single fraction. What is this guy equal to? I just want a single number right now. What's the final limit? Isn't it 1 over 2? Because the n squared and the n squared are the same power, so we just look at the coefficients. So it's 1 over 2. I claim that we could have done that without actually distributing the n plus 1 squared out, because if it was like n plus 1 to the 5th, I definitely don't want to distribute it. The fact is, all I need to know is what is the highest power. So if you distribute out the n plus 1 squared, but you don't actually do all of it, clearly n squared is the first term, right? Plus lower order terms, right? Terms we don't care about, possibly lots of them. So that's all we need. You don't need to actually do any distributing. And so as soon as I know the top is an n squared and I say, hey, the bottom is an n squared, it's really just about the 1 and the 2. Okay, last one has factorials in it. Let's give that a try. Go ahead and do your first step, where you flip the bottom fraction over. Okay, so let's give this a shot together. Limit n goes to infinity. So copying the top one, flipping the bottom one. Okay, what happens with the 4s? Single 4 where? On the top. More 4s up there, more 4s up there at the end of the day. Okay, now we've got an n factorial over an n plus 1 factorial. And you remember, we did stuff like this the other day exactly to prepare us for this moment. Remember how they cancel? That's right. So the idea was that we would write out the stuff from the bigger factorial. In this case, it's n plus 1 times, what's the next term after n plus 1 if I'm listing it out? Yeah, next one is just n, right?
Oh, right.
Okay, it goes backwards. N, and then n minus 1, n minus 2, but I can capture the rest of them with a factorial just on the n. And the reason I stop there is because, hey, I'm ready to cancel the n factorial on the top. So we just get 1 over n plus 1. Yeah? And so that n plus 1 just ends up right there on the bottom. Yeah, and in this case, the higher power of the n is on the bottom, then they don't cancel like they did before. So this is 4 over infinity, 0. Any questions on those 3 limits?
I guess I'm a little confused with the, how you get the one.
Yeah, so the n factorial on the top and the n factorial on the bottom cancel.
Wait, no, I mean, I get that. I just don't have, you pull it out. I know it's there too, like I don't get how you get from that first part to the second.
So if you had, let's say, like 4 factorial over 5 factorial, which is that pattern where the number on the bottom is 1 more.
Right.
Okay, so 5 factorial is really 5, 4, 3, 2, 1. And 4 factorial is 4, 3, 2, 1. You're just left with the 5. But instead of writing it that way, the way that we've written it up above is we kept the 4 factorial intact. We represented the bottom as being 5, and then everything else. Okay, I think that is good. Go ahead and move on to the activities that start on the next page. You are going to want to use the same format for your proofs that we did right there in number 8. Right, so your proofs are going to look just like the ones we did in number 8.